because this is as cold as it gets in São Paulo. So we start the third lecture of Roman today.
Thank you. All right. So yesterday we discussed the growth of structure in the linear approximation, and let me just recap. We saw that the linear growth for density and velocity divergence, so this guy was minus the divergence over Hubble. Can be written as some growing mode and some decaying mode acting on the initial conditions. And this was assuming that we are still in the approximation that we are still not close to the time when the universe starts to accelerate. Once things get closer to dark energy domination, then you have to, the solution of the growing mode becomes a function of A or a function of time, which is called D+. And this is some kind of hypergeometric function. Okay, it's quoted in the notes. It's not very illuminating. Okay, you can also solve it numerically. The decay mode, you can see, is a to the minus 3/2. You can show, so for omega matter equal to 1, the Friedman equation says h squared is equal to rho, which is a to the minus 3. So you can see Hubble is a to the minus 3/2 when omega matter is all there is, right? But it turns out this is also true when you add a cosmological constant, and even if you go beyond a flat universe. So the decay mode is just the Hubble constant, okay? Now, in that case, in the case where omega matter is not equal to 1 and you also have a cosmological constant, this guy gets defined in a slightly different way. So here appears something called the velocity growth factor, little f. So f is the log derivative of the growth factor with respect to the scale factor. Okay? So that means that the true velocity divergence, right, so which I called theta before, will be minus h f theta, big theta, okay? And this is very important because this is called the growth rate, because it's the growth, the log derivative of the growth factor with respect to log A. And this is a parameter that has a lot of information on cosmology. So it depends on the matter content, omega matter, omega lambda. It also depends on the theory of gravity. So if you try to explain the acceleration of the universe instead of by adding dark energy to modifying general relativity on large scales, this growth rate will change, okay? And this is one of the ways, the best ways actually, in which we can test modifications of GR, okay? So in the case of a flat lambda CDM model, this parameter f is reasonably well approximated by the value of omega matter as a function of time to the power of 5/9. Okay? Just to give an idea, okay? So obviously, if omega matter is equal to 1, right, this growth factor becomes A, so this log derivative is equal to 1, right? So this becomes equal to 1, right? when the universe starts to accelerate, the growth slows down, okay? And you can show this F goes from 1 at high redshift to essentially half by today, okay? So we'll talk about later how we actually can measure this from observations, okay? So this we will talk about on Friday using so-called redshift space distortions. All right, so this is then the linear growth of perturbations, okay? So now let's go nonlinear. Let's now try to incorporate more physics. So since the fluctuations are growing, remember the rationale for using linear perturbation theory was that at high redshift, at early times, we know perturbations are very small, so we can linearize the equations of motion. But because perturbations are growing, once the universe becomes matter-dominated, then eventually this assumption that the perturbations are small eventually, ceases to be correct, and nonlinear corrections will become important, okay? So one way of calculating this is perturbatively, as long as fluctuations are still smaller than unity, but not 10 to the minus 4, we can get some understanding from analytic solutions of the equations of motion in an iterative fashion. And this is what we call nonlinear perturbation theory, which it became now known as standard perturbation theory. So many people, if you read papers, they will call this SPT. And again, I'm going to start from the case where omega matter is equal to 1, where things can be done analytically very easily. And then I'll tell you at the end what happens when you include a cosmological constant. So I'm going to rewrite again the equations of motion that I wrote yesterday, now using log A as the time variable, which you can always do, and using this capital theta as my velocity divergence. So it's also a nice way of writing things. And linear perturbation theory will be, what we did so far, will be equivalent to setting the right-hand side of these two equations equal to 0. So now this will be the term that we neglected yesterday, where now U is a normalized velocity field. Okay, in the case of omega matter equal to 1, F is equal to 1. Okay, so it's just minus the velocity field divided by curly H. And then we have the Euler equation, or the divergence of the Euler equation. So again, this is the Euler equation equal to 0 that we solved yesterday. So this is the Poisson term. This is the drag due to the expansion of the universe. And now on the right-hand side, we have the nonlinear term that we neglected yesterday, okay? And we are assuming, in Fourier space, we are assuming that vorticity can be neglected, which is also true in the nonlinear case. Maybe later I'll discuss, if there is time, how vorticity grows. It's actually pretty negligible for anything we are gonna do at large scales. So that means the velocity mode only has the divergence part, the scalar part of the flow. Okay. So so the way we are going to solve this is by going into Fourier space. Okay. So now I'm going to Fourier transform these equations, and we'll see something interesting happening. So the non-trivial thing in Fourier space, so now we are going to have to write this u, this velocity u, in terms of the scalar. So we get an equation for two scalars, the same thing we did yesterday, which we didn't need to do much because that was already in terms of two scalars, okay? So now using this, we can rewrite the right-hand sides in terms of the velocity diversion scalar, okay? And there will be some Fourier structure here, right? Because gradients become multiplications by k vector, okay? And the velocity has this structure as well, okay? So now the right-hand side is going to have some Fourier vectors appearing, okay? And so that structure, and the other thing you have to notice here, these are at the same location, right? But it's a quadratic nonlinearity, so when you Fourier transform, if you remember your Fourier transforms, the Fourier transform of a product is a convolution of the Fourier transforms. So there will be some integral on the right-hand side, which will be a convolution so remember, K12 is the sum of two Ks. Then there will be, oh, this is the worst place to have a discontinuity. So, okay, let me see if I can do this. So there is some coefficient there, alpha K1 of K2, okay, which describes this Fourier structure having to do with this scalar product between this guy and this guy, okay? And I'm going to tell you what it is in a second. And the Fourier transforms of these two fields, okay? And you can see this is a convolution, right? Because this K1 plus K2 from this delta Dirac here has to sum up to K, right? That's another way of writing a convolution, okay? And similarly for the other one. So we'll see that this looks maybe a bit complicated, but it's actually not that hard once you stare at it long enough. So the other equation will have a slightly different coupling function, beta, let's call it, very original, alpha and beta. Okay, and just from the structure that we have of these gradients and so on, these functions, these coupling functions that couple two Fourier modes are relatively simple, and they are dimensionless functions. Okay? So that just comes from this structure, and the definition of U. And so basically what it does is something that now it's obvious from these equations. In the linear regime, what we solved yesterday, because the equation is linear, each Fourier mode evolves independently. Now we see through the right-hand side here from these nonlinearities, the Fourier modes are talking to each other. And they're talking to each other through these alpha and beta functions, okay? And so that's what we call mode coupling. Delta D is the Dirac delta. Yeah. So it's a constraint that the sum of the two Ks had to add up to the K mode that I'm looking at. Yes, thank you. All right. Yeah, so these guys are called the mode coupling functions. Okay. And so what we are going to do is we are going to solve these equations perturbatively, right? So we already know what the linear solution is, right? So then I want to find the second order solution. So I want to find these guys at second order. What I'm going to do is I'm going to put on the right-hand side the linear solution that we found. Okay? So we treat the right-hand side as a source for the left-hand side. We put in the source terms the linear solution. We will find a second order solution that will be quadratic in the linear solution. Okay? Now, once you find the quadratic solution, you go back. Now you put on the source term things which are cubic in the linear solution, meaning second order, first order, plus first order, second order, and the same thing here, and you will find the third order solution. And you keep going, keep going, keep going, okay? And when you do that, you can see that each time I go one more order in perturbation theory, I'm gonna have, for now, let's think only about the growing mode, okay? I'm gonna have an extra power of A, okay? So the second order solution, the fastest growing mode is gonna go as A squared. The third order solution, the fastest growing mode is gonna go as A cubed, and so on, okay? So you can show that you can solve that this a self-consistent solution for the fastest growing mode at each order in perturbation theory is to say that this guy will be some sum over n's. So linear order up to infinity, if you're brave enough, will be a to the n for the fastest growing mode times some function of k, which I'm gonna call delta n, okay? Where this will be for n equals 1 is the fastest growing mode solution we had there, okay? And so on. For second order solution, okay, will be a squared times a function delta 2 that I had to find from these equations. And the same thing for this normalized theta divergence. Now, what we found over there is that restricted to the fastest growing mode, when n is equal to 1, theta and delta are exactly the same, right? If you restrict yourself, if you kill the decaying mode, the growing mode is the same. If you remember, this matrix is this. So it's the same for densities than for velocities. Okay? So you just plug in these ansatz and check that that solves the equations, okay? So let me just quote the results. So if you plug this on the left-hand side and on the right-hand side, what's going to happen? On the left-hand side is pretty easy because everything is just a linear, okay? And derivatives log a with respect to a to the n just brings down an n. That's all there is to it, okay? And on the right-hand side, things get a little bit more involved, right? Because you have two sums, right? But you can collect the overall power of a to the n to match it to the left-hand side, right? And so you collect powers of a to the n here, a to the n there, because the time dependence is arbitrary. At each order in a to the n, you should match the coefficients on the left-hand side and on the right-hand side, which only depend on k. And so that determines a recursion relation for these functions, okay? So when I do that, I collect powers of a to the n. The first equation, you can see now the log derivative brings down an n. And on the right-hand side, I have all the ways that this product can sum up to a to the n. So I can have let me put it here first. I can have n minus m order in the density perturbations, and then m order in the velocity perturbations, and that adds up this plus this index as up to n, so that will go as a to the n as the left-hand side. And then, of course, I will still have the mode coupling functions, the delta function, which I'm going to write like this. Okay, it's always the same delta function I have over there. And of course, I have an integral over K1 and K2, okay? And then the same one here. I'm going to multiply everything by 2 here, so let me multiply by 2. Just for simplicity. So then I have 2n plus 1 times theta n. Okay, so it will be, this becomes an eigenvalue n, 2n plus 1, okay? And then I have minus 3 delta n. And then same situation. The only difference now I have, instead of alpha, I have beta. And now, because it's the Euler equation, I have 2 thetas, 2 velocities. Okay? So this looks maybe a bit horrible, but it's actually pretty simple. It's a recursion relation, right? So if you start with n equals 1, this is the solution that we solved yesterday, right? So the right-hand side should be 0, and you can see, in fact, if n is equal to 1, this sum disappears, right? So when you try to solve the second-order solution, n equals 2, there's only one possibility you're going to get a square, and is if m is equal to 1 and n is equal to 2. So this is linear, 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 okay? And so on. So we can write this in matrix notation, right? The same thing we did over there, okay? So let's write it in matrix notation. So this is some matrix, which is n minus 1, minus 3 to n plus 1. So now I'm going to skip the arguments, so I don't need to write everything. Okay, I'm skipping all the arguments, but it should be pretty clear. It's the same arguments I had over there. I just write it in matrix notation. So now, in order to solve for these guys, right, as a function of the previous ones, right, I just invert this matrix, and we're done, okay? And so that's the inversion of the matrix. So here's the determinant, the inverse of that matrix, multiply the source. Okay, so this is evaluated at K2. These guys are at K1. And alpha and beta are functions of K1 and K2, okay? So this is the famous recursion relation for solutions to arbitrary order in perturbation theory. And you can see that because we have these quadratic nonlinearities, as I mentioned, delta second order and theta second order is going to scale as first order perturbation square, okay? And as I said, first order perturbations are equal for the fastest growing mode. They are equal to each other, so we can just use delta 1 because they is equal to theta 1. And so you can rewrite this. The solution to nth order is going to scale as delta 1 to the n. And you can write this in a maybe this I need for later. So let me do it here. Continue here. So you can write this recursion relation in a slightly more friendly way by introducing the perturbation theory kernels. And this is what we are. So the nth order solution is going to be given by n Fourier modes Q1 through Qn, okay? Because of mode coupling, these guys had to adapt to the k that I'm interested in. So there will be here a momentum conserving delta function. So maybe write it like this, sum of the Qi's from 1 to n. Okay? And then all the nasty thing here, the only nasty thing here, there are numbers, okay, which are nice. And then there are these alphas and betas, right, which are functions, ratios of k's, as I wrote earlier. So that will be some kernel, which is dimensionless, made out of all these alphas and betas, which we are going to call Fn for the density perturbations, and same situation here for the velocity perturbations with a different kernel. Yeah. Yeah, so this integral here is over K1 and K2. Yeah, here is over all the Q's, yes. Thank you. Thank you. So, and of course, if you evaluate this for n equals to 1, it's an equality and means F1 equals to G1 equal to 1. Okay? All right? Yeah. What's the definition of Q? Q is some arbitrary momentum, right? Arbitrary Fourier space momentum, right? And it's being integrated over, okay, in both cases. And they have to satisfy, this is describing mode coupling between different Fourier modes. So the nonlinear solution at order n at Fourier mode k is made out of all the possible linear guys that through this function coupled to add up to k. Okay? And these guys are made out of these alphas and betas. Okay? So let me give you an example, because it sounds pretty horrible, I admit. Although the more you work with it, it becomes your friend in some sense, yes. Yes, good question. Sorry, I forgot before to repeat the question. So, yeah, because of this property, which I erased already, theta 1, remember theta 1 is the same as delta 1. So here I'm using delta 1, okay, because it's the same. Yes, yeah. Okay? Good. Now let me give you this, it looks very non-intuitive maybe, okay? The first time I saw this, it's like, what the hell is going on? You're probably thinking the same thing, okay? So let me give you the first non-trivial kernel, which is the second order solution. Now, what I'm about to do is all the physics there is in these equations, okay? So this is a great deal I'm giving you. I'm going to only give you n equals 2, and I'm claiming this is all the physics there is in these equations. Why? Because remember, the equations have only quadratic nonlinearities. So just by looking at the second order kernel, the physics of these nonlinear terms is already there, okay? What higher orders will do is to improve the description of these quadratic nonlinearities. But there will be no new physical effect after n equals 2. Okay? So that's very important. So let me write, if you do this, you follow the algebra, okay? It's one of the homework problems that I put on the web page. So you can derive the second order solution. And remember, these guys are dimensionless functions of K1 and K2, or Q1 and Q2. So I'm going to decompose it into Legendre polynomials, okay? So the first term will be the monopole. Look at that. That's a nice number, 17 over 21. The second term will be a dipole. So it's just the scalar product between the unit vectors Q1 and Q2, and then some ratios of these magnitudes. And the last term will be a quadruple, L equals 2. Another nice number, 4 over 21. And then the second order, the second Legendre polynomial. Okay, L2 of the cosine of the angle x is just 3x squared minus 1 over 2. Okay, that's the usual Legendre polynomial. Okay, now G2 is the same thing, looks very similar. The dipole is the same, and then the last term, just different coefficients, okay? So what does this mean? Okay, so I'm claiming encoded in these three multiples is all the physics there is to these nonlinear equations. Okay, that's a pretty big claim. So let me try to justify it. Two-thirds. Yeah, what I'm doing is I'm actually putting n equals 2 here and doing the math, yes. And I assign it to you as a homework problem, okay? Check the exercises. It's something you should do once in your life, okay? And the way I'm trying to sell it to you is a worthwhile exercise, because you will learn all the physics that there is in these equations just by doing the quadratic solution, okay? Higher order solutions will only slightly improve the description of the nonlinearities, but no new physical effect will appear. So let's now try to interpret the monopole, the dipole, and the quadrupole. Of course, each of them will have a different physical origin. Yes? Yes. 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 Huh? Yeah, so the claim is that when I solve this, right? Let's do the second order, okay? And you will see how it happens, okay? Put n equals 2 here, right? So this is some numerical matrix, right? And then here, m can only be 1, right? Because it goes from 1 to 2 minus 1, 1, okay? So 2 minus 1, 1. 2 minus 1, 1. This is 1, okay? Now, all these guys are 1, and delta 1 and theta 1 are exactly the same, okay? So that means this becomes delta 1 of K1, delta 1 of K2, right? With some alphas and betas, right? And that's exactly the F2 kernel, right? So if I put n equals 2 here, this becomes a 2, right? And it will be delta 1 and delta 2. No, sorry, delta 1 of Q1, delta 1 of Q2, right? And so this guy will be a linear combination of alpha and beta, 5/7 of alpha plus 2/7 of beta or something like that, okay? Which these 5/7 and 2/7 come from that matrix. Yes, iteratively. Now put n equals 3 here, right? Now you have two possibilities. M can be 1 or 2. You have to add them up. And this will involve delta 1s and delta 2s, and theta 1s and theta 2s, which you already have from the previous solution we just did. Keep doing it. And you will find that, of course, it will be written in this form. OK? Good. Good. So let's go to the physics, OK? Enough math here. So what is the monopole? What is the dipole? What is the quadrupole? So just a reminder of what the linear theory is, right? The linear theory is just the initial condition, delta 1, okay, which is these Fourier modes that are coming from inflation plus radiation error effects, right? And if you restrict to the growing mode, it's just scale it by A, right? So trivial, just scale it by A, nothing more, okay? So that means if I have some density perturbation here, in linear theory, it just increases the amplitude without changing shape and without moving whatsoever, right? Because I'm just scaling everything by A. It doesn't change shape. It just increases the amplitude. It doesn't move at all, okay? Now, these guys are more interesting, right? So let's look at the monopole, okay? What is the monopole? How do you get the monopole out of the general solution? You just spherically average, right? If I just spherically average, the multiples average to 0, right, by orthogonality of Legendre's, right? And so this guy, the 17/21 or whatever for the density and the 13/21, describes the spherically averaged dynamics. And this is what we call in cosmology the spherical collapse model. So if you had an isolated spherical perturbation and you solve it assuming spherical symmetry, what you will find is that each ordering perturbation theory will be the monopole. And so the spherical collapse dynamics, which you can actually solve non-perturbatively, at each ordering perturbation theory will be some, delta 1 to the nth power times some pure numbers. And this monopole is actually generating that solution in a perturbative way, okay? So the interpretation of this, of the monopole, is just the spherical collapse dynamics. So that means now suppose I have my initial conditions and I put some spherical perturbation, okay, which I'm gonna draw schematically that, and I put it at some location, centered at some location. That's my initial condition, right? In linear theory, this guy will grow, okay, which means that it will be collapsing without changing shape, okay? So in linear theory, at a later time, as I evolve using linear theory, this will collapse in some, I'm assuming here that it's positive perturbation. So it will collapse in some fashion. So it's gonna become smaller. But it's not changing shape, and it's not moving, right? Because linear theory is just a multiplicative factor, okay? Now the monopole is also a multiplicative factor, right? Because it's this times delta 1. When this guy is just a number, this becomes delta 1x squared if you do it in real space, right? So that means if I now add this L equals 0 second order, it just corrects the linear growth, but it's still spherically symmetric because it's the monopole, right? And it's a bit stronger because it grows as a squared instead of a, so it will make this collapse even a bit more, okay? So let's make it a bit smaller. So this perturbation is growing a bit faster. Does it make sense what I'm drawing? Okay? Good? Okay. Now, what is L equals 1? So this is the dipole, L equals 1. Let's add L equals 1. What is the dipole? Any guesses? Huh? No, so a dipole is just a translation, right? So a dipole is coming, remember from the equations of motion, I have this, v dot gradient, right? What is v dot gradient? It's the time derivative when you're following the fluid, right? So the dipole is a displacement. It's in the CMB, right? When we are in the CMB and the observer is moving, it's a dipole in the CMB, okay? So it's the same thing. So the dipole is just the fact that now we are including mode coupling, right? And so that means this guy, this perturbation says, wait a minute, there are other perturbations around, and they say there is more matter here than here, so my overall gravitational attraction is to move in some direction, okay? Which direction will depend on the linear fields, okay? So that means once I add L equals 1, this guy actually moves, let's say moves to the right, okay? So that's the dipole, the physics of the dipole. It's just a displacement because there is more gravity. I'm being pulled by gravity more from that direction than from this direction. So I just move a little bit, okay? Finally, the quadrupole, and then this goes to one of the suggestions before. What is a quadrupole? A quadrupole is a tidal effect, okay? It's like tides, okay? Like, you know, the tides due to the moon, okay? It creates a quadrupole effect. So that will change the shape of this guy. So if originally it was spherical, depending on what the structure of this against the initial perturbations will make now this guy. Let me exaggerate this so I can draw this better. So now this guy moved. And now once I L equals 2, it changed shape without changing volume, okay? So these guys change the volume. This guy is an overall displacement. This guy, without changing volume, changes the shape due to tidal effects, okay? Any questions about that? This is very important, okay? This is all the physics in the nonlinearities. Okay? Yeah, so the reason why I claim there is no more physics than this is because there are no cubic terms, there are no quartic terms in the equations of motion, right? So no new terms will show up once I go to third order. All the terms already showed up. What perturbation theory is doing when you go to higher orders and higher orders is to improve in the description of these guys, right? Because the way we solve for these quadratic solutions is to plug linear solutions here and then solve on the left-hand side, which is not truly self-consistent, right? So it's trying to fix it and fix it and fix it as you go to higher and higher orders. But it's just an improvement on the description of these three effects, right? So for example, for the spherical collapse piece, you know, the spherical collapse doesn't grow as a plus a squared, right? It grows as some function of a, which is some kind of, I don't remember how to describe it, but it's like a closed universe solution, right? And so it will improve a cube to the fourth, and eventually, once you sum up all the orders, it will sum up to the solution of the spherical collapse, right? And the same thing for the others, okay? Yeah. Yeah, the difference between linear and L equals 0 is just this will grow with respect to the initial condition as a, and this will grow as a squared. So it's making the collapse faster, okay? With this coefficient here. Yes? Yeah, so I'm adding. Yes, I'm adding. Sorry. Everything is being added up. So by the time I got here, I already added the linear solution and the three multiples of the second order solution.
But the system ends before and translate.
Yes, yes. Yeah, so you can see this guy compared to say the correction to the linear is to collapse it a bit more, shift it, and then change the shape, right? And then as you go to higher orders, you will see the same kind of physics. And each of these effects will be slightly different. Okay, will be some correction to this. Yes? Maybe I'll get to describe the Seldovich approximation. It's these coefficients become 1/2. Okay, so it doesn't have the right spherical collapse. It doesn't have the right tidal field. Okay, but the dipole part is the same. This cannot be changed because this is just by symmetry. It has to be of this form by Galilean invariance. So this is fixed. Yeah, that's why there is no number there. In fact, these numbers can depend on cosmology. This number is fixed at all by symmetries. Yeah. Okay, so, all right. So, yes. Huh? Sorry, I cannot hear you very well. Yeah, because I'm looking at the fastest growing mode, okay, and in that case they are the same. Huh? Yeah. So I'm always at each, in order to show this solution, I'm always taking the fastest growing mode at each order, okay? And this is the claim that, which may not be obvious from here, that if you actually put the decaying mode, okay, in the linear solutions, this is still correct for the fastest growing mode in each order in perturbation theory, okay? So, yeah, maybe I can answer that in the Q&A later. We can discuss it in more detail, but it may not be obvious that if I include the decaying mode, this is already including the decaying mode, except that delta 2 will not just grow as a squared. There will be slower ones, but these solutions, if I look at the fastest growing mode for quadratic order or cubic order, is still correct, okay? Yeah. It doesn't matter. It doesn't matter. Yeah, you can choose here an initial conditions which is not the 1, 1. And I'm saying even if you do that, this is still correct for the fastest growing mode at each order in perturbation theory. So on top of this, there will be terms that say for n equals 2, they will grow less than a square, okay? But I'm not keeping those, okay? Okay, so good. So these kernels have some interesting properties. So for example, you can see that if I evaluate a total momentum equal to 0, these guys vanish, okay? So if I evaluate Q minus Q, these guys will vanish, okay? And that has to be the case, right? Because remember, these guys are fluctuations, so their mean has to vanish. So if I take delta 2 and I take expectation value, by translation invariance, Q1 has to be equal to minus Q2, right? And the only way that can vanish is if this guy vanishes and this guy vanishes. So these guys always vanish, okay, if the sum of all the momenta for any n add up to 0. They also satisfy some important properties. If the total momentum is, so you can see here, K is my total momentum, is the sum of these two, right? As I take the total momentum going to 0, these have to vanish as K squared, and this is the result of momentum conservation. And this is, again, true for all Fn's, not for the Gn's. This is just for the density. And the last property is what is known as it's coming from Galilean invariance. So if I have now a soft mode, so I have a P going to 0, but it's not the total momentum, okay? So I have arbitrary case here, and the n plus 1 is some P going to 0. you can see that there are these poles here, okay? And that's dictated by Galilean invariance. And so this has to be, there is a pole in the soft momentum P. So as P goes to 0, there is a, it has to go like that, plus order P to the 0, okay? So this pole is related to these pi soft theorems in field theory and so on, which I cannot get into now. But this is what we call the squeeze limit, okay, where one momentum goes to 0. All right, so that's the solution, okay? Now, remember yesterday I told you, well, these decaying modes are interesting, okay? And as I was claiming 5 minutes ago, if you actually include the linear decaying modes without, when I made the ansatz that the solution to these equations iteratively should go as a to the n, all I'm doing is saying that after you do the calculation in the most general way, if you keep only the fastest growing mode at the end of the calculation, you will find this, okay? But that means I'm also including linearly decaying modes, okay? So for example, if you do the calculation by starting from here, okay, and trying to do it by integrating over time and so on, you will see that if I ignore completely the linear decaying modes, okay, which I'm not doing here, then this coefficient becomes 11 over 15, for example, and this becomes 4 over 15. So if the physics of the linear decaying modes is ignored, you will actually make about a 10% error in the monopole and about a 30% error on the quadrupole, okay? So that's, and this is something that many people actually that work on this actually don't know. So I'm telling you some secrets. It's in some very obscure paper I wrote more than 25 years ago. Okay. So, and you might think, well, how can this happen, right? Because the way you can think of the second order solution is I have two linear modes that they propagate in time, right? Then they interact, and they get coupled by this alpha and beta, and then afterwards they get propagated again by this linear propagator. Okay? And you have to take into account this interaction between these two linear modes. When I'm looking at the second order solution, it's just two linear modes that grow from the initial conditions. They interact through this alpha and beta, and then they propagate again linearly afterwards. Okay? Now, even if you start with growing mode initial conditions, after they interact, because alpha and beta depend on k and so on, they will not be in the linear growing mode anymore, right? And so once you integrate in time until the final time after the interaction, they will have some contribution from the decaying mode. Now, this interaction can happen anywhere from the initial conditions until the final. So when you integrate over time, you realize, because of the growing and decaying modes, that the integral is dominated by the last bit. So the decaying mode still contributes a little bit. It's dominated by the last bit, and it contributes, it contributes some small fraction, but it's still a non-zero answer. Okay? So, all right. Okay, so now let's see what happens when we approach acceleration of the universe, right? Then you can show that these solutions, you can write in a similar form to a better than 1% accuracy. You can write them in the same way. So now instead of a to the n, I'm going to have the growth factor to the nth power. And for theta, I'm going to have the same thing. And so all these guys are, again, the same guys to a very good approximation to better than 1%, the same recursion relations I derived there. And all the cosmological dependence is included here. Okay, this is an approximation, but it works to a fraction of a percent, so it's pretty good. In fact, so far we didn't need to go beyond this approximation at all. Okay, so any questions? Yeah, so we'll get to that in a second, yes. One question is, these things keep growing. Eventually, the whole thing is going to explode, right? So perturbations will be so large that this iterative procedure is not going to work, okay? So that's what I'm going to get into now, yeah. Any other, yeah. Yes. No, Galilean invariance means, right, it means that if I do a boost, right, the physics should be the same in any frame, right? It's actually more interesting than that. It's not just the true Galilean invariance. It's just a boost where the velocity is constant in time. Now here there is gravity, right? And so underlying gravity is GR. We have the equivalence principle, right? So you can always move to a frame which is the Einstein elevator, which is falling in free fall, and the physics there should be the same. So actually, the Galilean invariance that is true for a fluid, in this case, because there is also gravity, is enhanced, and the boost that you do can actually depend on time. So it can be an accelerated, change into an accelerated frame. So, yeah. And so there are lots of interesting things about that that I don't have time to discuss. But yeah, so some of the symmetry properties of the kernels, like the way this looks like, this property over here, are related to this, yeah. Okay, so now the obvious question is, what is this good for, right? At the end, okay, it's nice to solve these equations, whatever, but we want to use it for something, yeah. Yeah, so this guy is saying that the solution at second order at mode K is coming from the coupling of two modes with arbitrary momenta such that they add up to the K mode that I'm looking at, okay? So if I'm looking at some particular wave, right? In linear order, that wave doesn't change wavelength, right? It just increases in amplitude like in linear theory, right? But a nonlinear order, this wave knows about this other wave and this other wave. And as long as the sum of the two Ks couple is the same as the wave I'm interested in, it will have an influence, okay? And so that's what we call mode coupling, yeah. And as you can see already from this answer to this question, if there is coupling between modes, now the shape of the power spectrum is going to change, right? Because a linear order, the shape of the power spectrum is just scaled by a square, or growth factor square. Now, if different Fourier modes are talking to each other, then the evolution at nonlinear order at one particular K is going to depend what all the other K's amplitudes are, okay? Now, the most dramatic change in going from linear to nonlinear K's is generating non-Gaussianity. So that's the thing I want to discuss now, how nonlinearity implies non-Gaussianity, and try to get to use all these solutions to actually do computations of how non-Gaussianity gets generated by gravitational evolution, okay? So to recap, if you have linear theory, because you're just scaling by a scale factor without changing any shape, if the initial primordial fluctuations are Gaussian, then remain Gaussian, okay? They just change the power spectrum by a square, or the width of the Gaussian by a square. It's just a different width of the Gaussian, but it's still a Gaussian, okay? So, but of course, things become more interesting once we include nonlinearities. So let's see that how we develop non-Gaussianity after Gaussian initial conditions. So now, as you can imagine, I can start from these equations and derive how you get a non-zero bispectrum and so on. That will be something I'm going to do eventually in a simplified way. But if I do that, it may obscure the physics. So let me start really, really simple. Before we go into the technical answer, let's develop some physical intuition of what's going on, okay? So we have Gaussian initial conditions, right? So as we discussed and also Gonzalo mentioned, that means at a single point, right? If I do a histogram in my random field and I collect all the values of the density perturbation delta, obeys a Gaussian distribution with some width sigma square. Okay, sigma square is the 2-point function, which for a single point is just the average of delta square. And to make the thing obvious, I'm going to draw the Gaussian here. Okay, and sigma square is the width of this at half maximum. Okay. Now, a Gaussian distribution has an obvious symmetry, right? It's the symmetry of delta going to minus delta. Right? Now, this is very important, right? Because that means if I draw a random field, which is Gaussian, I cannot do anything I want, right? It has to respect this symmetry. So that means if I point to an arbitrary location in a random Gaussian field and I ask, is this overdense or underdense? As I average over all space, I better get that there is the same number of points in a Gaussian field that are overdense, that are underdense. Okay? Is that clear? Even more than that, if I ask, there should be the same number of points which are underdense by 30% and by plus 30%. Okay? So I have to have the same probability here that I have there. So you can see how a Gaussian field is something very, very constrained, very special. Okay? So if you are given Gaussian initial conditions, you should be very appreciative. Nature has been very nice to you. Okay? Now I'm about to mess it up with gravity. Okay? So let's see how that happens. First, it's obvious under linear theory, this gets preserved, right? Because each Fourier mode evolves independently just by a multiplicative constant. So all it happens is this width grows as a square. Gaussian becomes still Gaussian, okay? So that means if I now take a random Gaussian field and I apply linear theory, all it happens, the overdense regions become more dense, the underdense become more underdense, but the counting between overdense and underdense still respect this symmetry. Now, nonlinearities break this symmetry, okay? Because now I have my equations of motion, right? In linear theory, I have, things like this, right? Linear in this, linear in that, right? If I change the sign, that's still the same equation, right? Once I add terms which are quadratic, if I reverse all the fields, that's not a symmetry anymore, okay? And so you can see how quadratic nonlinearities are going to break the symmetry that will preserve a Gaussian, okay? Just without doing anything like this, just from the shape of the equations of motion, we can predict something interesting will happen, okay? Now let's think a little bit more about the physics. Remember I told you that the physics of these equations can also be thought as gravity competing against the expansion of the universe, okay? So now if I look at underdense regions, which are at delta negative, so these are underdense regions. Sorry, this chalk is not very visible. And let's look at, in order to look at the symmetry, I'm going to look at underdense regions and overdense regions. Okay, so in underdense regions, gravity is weaker, right? There is less matter. So the expansion of the universe will win against gravity. Okay, so here, underdense regions, expansion wins, to put it in a simple way. Here in overdense regions, gravity wins. Okay? So let's think now what happens. If I have an underdense region, right, because the expansion of the universe wins, that underdense regions will increase volume at later times. Okay? Whereas now in an overdense region, gravity wins, will decrease volume. So now if I evolve my Gaussian perturbations forward in time, if I now point at arbitrary locations and my final conditions, because most of the volume will be occupied by underdense regions, it's most likely I will have more points which are underdense than overdense, because the overdense ones contracted, so they occupy less volume because gravity won there. The underdense expanded. So that means automatically that this probability distribution at late times, the most likely value in a Gaussian field because of symmetry is to be at the mean density, delta equal to 0. Now because the underdense regions have expanded, the most likely overdensity that I'm going to hit most often is going to be a negative one. So the peak of the PDF is going to shift to the left. So this maximum, which before was at 0, now is below 0. Does that make sense? Yeah. Yeah. So I'm looking at underdense regions and overdense regions, right? So if I have a region in the universe which is underdense, right, there the gravity is weaker because the amount of mass there is, by definition, under the mean, right? So that means the expansion of the universe is going to win against gravitational attraction. So that region will actually increase volume as time goes on, right? Whereas a region which is overdense is the opposite. Gravity wins, is going to decrease volume. So this symmetry that I have originally, that it was equally likely to have underdense and overdense regions, now this balance is lost, right? Because most of the volume on the universe is going to be occupied by underdense regions because they grow in volume, where overdense regions, they contract in volume, okay? So that means if I point at a random point in the sky, and this you can do, go at night and look and just point, okay? And see how many times you hit an overdense region and an underdense region, you will see most of the time you will hit underdense. So the most likely value to hit will be an underdense region, okay? Now, compared to the Gaussian field, because in high density regions, things are collapsing, the density that I will have once I hit an overdense region will be much higher than in a Gaussian field, right? So that means this tail to high delta will be enhanced, okay? So that's the physics of it, okay? So this is enhanced right tail because of collapse of structure, so you will have high density much higher than in a Gaussian field. Okay? And these are essentially the void regions dominate. Voids are the underdense regions dominate the volume. Okay? So you can see now, wait a second, I'll finish one thing. You can see now that if I calculate now the third moment in a Gaussian distribution, by symmetry is 0, right? Because doing this integral. This is symmetric. Under inversion, this is anti-symmetric, so this is 0. Now here, because of this asymmetry, you can see now I'm going to generate a non-zero third moment, or bispectrum, or three-point function. We already considered what? Yeah. Right, because essentially in the linear regime, you can see what happens. So suppose this is my mean density, and I have, let me draw an over density and an under density, okay? When I expand this by an overall factor of A, right, in the growing mode, all I'm doing, these nodes don't move, right? All I'm doing is just amplifying, sorry, I made my life complicated to draw the evolved one. Right, so the size, essentially the occupied, that symmetry is still there, okay? Whereas include A square, essentially on the nonlinear terms, what will happen is that this is gonna look like this, okay? And then this is gonna look like that. Okay, I'm exaggerating everything, but. Okay, any other questions? Yeah. Yes. No, this tail, you see there is something that I put under the rug, okay? Which is, remember the density field is the mean density times 1 plus delta, right? So that's the definition of delta rho over rho. This minus the mean divided by the mean gives me this. So because the density is positive definite, delta cannot never be more negative than -1. If you have a Gaussian PDF with large sigma, this tail can go beyond -1. Now, physically, this never happens, and that's a Gaussian fluctuation. A Gaussian fluctuation can only be true for small sigma, okay? And so what happens once you evolve nonlinearities, this tail becomes like a cutoff, and -1 is right here. So this drops like a rock, okay? So that's another nice feature that the physics, of course, captures. There was another question, yeah. What is what, sorry? Yeah, so the answer is it's a bit complicated, but roughly it is more or less, it depends. The answer to this question, you can see from the questions, it's a bit complicated. It depends of what's going on in neighboring regions and so on. But essentially, if you are well enough into an underdense region, the acceleration, the expansion of the universe wins. If you are well into the right, then always gravity will win. Okay. All right. So, any other questions? Okay. So. No, it's not. This is not 0. Sorry, this is a log-log plot. So, yeah. So it goes to 0 eventually. This is like, imagine this is, I don't know, here 10 to the minus 5 or whatever. It keeps going down. Yeah, I think I'm never going to make a plot which is not log-log, but. All right. So we can now, from these solutions, we can sort of understand, yes?
Short question.
Yes.
Is the main effect on non-Gaussianity in the PDF, or is just an example? It could be another kind of probability distribution.
No, it will look, I will show you, hopefully by Friday, I will show you the real thing. And you will see, yeah, I take a picture and compare with what I show you on Friday. You will see it's pretty, it will look like this, okay? So now, as long, as the more you evolve, the more this shift to the left, and this is more enhanced. And this is dropping like a rock more. Okay, so I just drawing as some particular time. So because this is non-zero, you can actually calculate. Since I'm running out of time, let me just quote the result. So we'll do it maybe if I get time, I'll do it. But you can show that this guy, if you calculate this now from the second order solution, you will see that the third moment scales as the second moment square. Okay, it's going to come from the structure of the equations, from the quadratic nonlinearities. And that's going to be 34/7. And this is what we call the skewness. Okay? And you can start to see this guy looks a lot like this guy. It's a factor of 6 away from this. Okay? So it has to do with the monopole of the F2 kernel. Okay? This shift that you see here, this delta max to lowest order in perturbation theory is minus S3 times the variance over 2. So you can see now what I was just saying, that as time goes on, this number actually doesn't depend on the growth factor. Okay? We'll see why in a second. Okay? So you can see the result doesn't depend on the growth factor. So it grows as the growth factor square. So as the universe evolves, becomes more and more empty, the empty regions, this shifts more and more to the left. Okay? Eventually, this leading order approximation, you have to correct it by higher order terms in sigma. But okay, so now, which may not be obvious here, is not just that you generate this. This shape it's maybe a bit ugly. I learned to like it, but it may look ugly to you compared to a Gaussian. But it has all the connected moments. Okay? So if you look at delta P connected, which is 0 for a Gaussian, it will be non-zero, and it will scale as delta squared to the P minus 1. And this is what we known as the SP parameters for P larger or equal than 3. Okay, so this is just an example of one of the non-Gaussian measures is the obvious one, the asymmetry, the lowest order asymmetry, but all of them get generated. Okay, for a Gaussian, this connected moment is 0. Okay? Okay, so now let me try to see at least how we get this number, and you will start to see arising from these equations how the non-Gaussianity can be calculated. Okay? So let's do it. Let's do a simple calculation. And then see what these kernels are good for. So our first order job is to calculate how this thing became non-zero, sorry. Starting from Gaussian initial conditions, right? So schematically, let's do it first schematically. So it will be the first order solution, the second order, the third order, et cetera, et cetera. Okay? I'm putting the growth factor inside these guys now. This goes as D, this D squared, D cubed, and so on. So we can keep track of how many there are just by the index there. So let's expand now. So to leading order, this will be the linear solution cubed. Then we will have 3 times this. Okay? Let's do a couple more. And I'm going to collect, since delta n goes as delta 1 to the n, I'm going to collect equal powers of the linear field. Okay, I'm almost there. And then you can see how non-Gaussianity shows up to. Okay, so I ran out of steam, so I did the first 4 terms. Okay, so the first term, delta 1 cubed, right? This one, delta 1 squared times delta 1 squared, so this is order delta 1 to the 4th. These guys add up to 5. Okay, 2 times 2, 4 plus 1, 5. 3 plus 2, 5. So these are order delta 1 to the 5, and these are delta 1 to the 6. Okay? Now remember, delta 1 is a Gaussian random field. So it only has even moments, right? So that means this guy is 0. Is that clear? Okay, that's just linear evolved, right? This guy, there are 5 deltas here. These guys are also 0. Okay? So the leading order contribution to the skewness, to this asymmetry, is going to come from this term alone. And then there's going to be some correction to it coming from the 6th order. Okay? So let's calculate this one. You can see this is a pretty nice thing, because we just need only the F2 kernel, right? Because it only involves 2nd order perturbation theory. Again, this justifies what I was saying before. At 2nd order, you already see essentially all there is to see. Yeah. Why this one? Because it's this, right? For a Gaussian field, remember delta 1 is Gaussian, right? So if I calculate this, right, I'm integrating a symmetric distribution against something that has, you know, anti-symmetry when delta goes to minus delta, so this is 0, right? So this is symmetric. It cannot have an odd moment. In particular, it cannot have also delta 1 to the 5, right? So that's what only this term, all the evens contribute, okay? Yeah. Because this is the perturbative description of the density field, right? Yeah, the sum linear theory plus quadratic order plus cubic order and so on. Okay, so that's what I was writing earlier, right? That delta is the sum of d plus to the n delta n k, and I'm absorbing these guys into here, okay? So I'm just writing this, okay? Good. All right, 5 minutes. Let's do it. I've done worse things in 5 minutes. You probably too, okay. So now, let's calculate delta cubed. Now I'm putting arguments, okay? I'm becoming more sophisticated, okay? So all the at the same point, okay? So now let's write the Fourier transforms, right? So I'm going to take as an approximation the lowest order. Okay? So now I'm just plugging in the Fourier transform of this guy and the Fourier transform, 2 Fourier transforms of this guy. Okay? So that's pretty easy. So there will be an integral. Let's do the delta 2 first. Remember, K12 is the sum of K1 and K2. So this thing is delta 2 at x, okay? If you remember my description of the kernels, right? I just need to Fourier transform this guy for n equals 2, right? With e to the ikx, and integrate over k. When I integrate over k, I use this Dirac delta, and the k becomes q1 plus q2, you know, f2 of q1, q2, okay? And then I will have the 2 linear deltas, which I'm going to put at the end. Okay? And now 2 linear ones, those are easy because it's just, let's call it K3, let's call it K4, integrate over K3, integrate over K4, and then plane waves at K3 and K4. And then I have expectation values. These guys don't care about expectation values because they are deterministic functions, so the only thing that is fluctuating are these guys. Okay? Questions about that? All right? So you're all ready to calculate. Sounds good. So now, remember, these guys are Gaussian fields, right? As we discussed, and as Gonzalo discussed yesterday, all you have to do is the 4-point function of a Gaussian field, this is not the connected one, right? You just decompose it into all possible pairs, right? For the endpoint, 2n point, only the even endpoint functions contribute, right, for a Gaussian field because of that symmetry, okay? So if you have the 2n endpoint function, there are 2n minus 1 double factorial pairs, okay? So in this case, there are 3 pairs, right? So this guy can be paired with this, or with this, okay? And the remaining pairs follow, okay? Now, out of the 3 pairs here, there is 1 pair that doesn't contribute, which is if I write the expectation value of this pair times the expectation value of this pair. Because when I put the expectation value of this pair, by translation invariance, this and this have to add up to 0. And this guy is 0 for that case, as we just discussed. What we are doing there is you are writing this. But because delta is a fluctuation, at any order in perturbation theory, it vanishes. So out of the 3 pairs, there are only 2 possibilities. I pair this with this, and that with that, or pair this with this, and this with that. Now, because of delta, these 2 guys are symmetric, these 2 give the same answer. So I get a factor of 2, and I just use 1 of the pairs, okay? And so that's the factor of 6 now. Now, because of translation invariance, at the end of the day, cannot depend on x, right? If I'm calculating here at one location in x, it should be the same at any other location, right? And you can see as you pair things, you will have 2 delta functions, and it will kill this sum of K1 through K4, okay? Because as in pairs, they have to add up to 0, okay? So that means the final answer is going to be, I'm going to have 2 power spectra. I'm going to be integrating over all case. Okay? So now you can see we are in good shape here. Now I have to come to this guy, right? Now I have to do this integral over d3k1, d3k2. But this guy only depends on the relative angle between K1 and K2. By isotropy, there are no angles here. So the only thing that contributes here is the monopole. So this is the same as 6 times 17 over 21 times, and once the monopole enters here, I just have an integral of this d3k1, an integral of this d3k2, which is the same integral, and that's the variance. So what I get, now writing explicitly the integration, I get this. So I get 34 over 21 times the variance square, which is sigma to the 4th. Sorry, 31 over 6, 7. So that's that mysterious number. Now we can see it coming out of the equations of motion. Okay? Now, you can see that this doesn't, okay, this is nice, okay? But this is non-Gaussianity described by a number, okay? There's not much information in a single number, okay? It's good to get that number right, okay? But we are missing all the interesting physics that I was spending a lot of time here explaining. We are only seeing the spherical collapse, right? So in order to see the rest, you have to undo the fact that everybody's at the same point, okay? So let me quote the result now, and I finish. Let me do it here. So instead of doing it in configuration space, I'm a Fourier space guy, so I'm going to do it in Fourier space. And this it's in the node, so now I'm going to calculate the 3-point function, but in Fourier space. And you can see what's going to happen. It's the same situation here, right? But now it's at a different point and in k instead of x, but it's the same idea. What's going to happen now is these kernels are going to show up in all their generality. So this thing is the bispectrum. And it will be an overall delta function by translation invariance. And the result will be and all the cyclic combinations. Okay, so by this I mean it will be 2f2, k1, k3, with p of k1, p of k3, and then 2f2 of k2, k3, p of k2, p of k3. So you can see now, once you undo the things that everybody's at the same point, then you get a non-Gaussianity measured by this bispectrum, which depends on the triangle shape. Okay, so you will have, okay, and remember by translation invariance, K3 is just, so it depends on the angle between K1 and K2, okay? And so the way the bispectrum depends on the shape of the triangle encodes all, you can see here, the dependence on the shape of the triangle encloses all this interesting physics that we discussed, okay? And it's the physics of gravity, okay? And so that is a lot more interesting than a single number, okay? And we will see by Friday how we can use the dependence on triangle shape to break degeneracies and constrain cosmology. All right, I'll stop there.
So more questions for Roman? Yes, so first there and then there.
Thanks, Roman. How does cosmological back reaction fit into this kind of picture?
Cosmological back reaction. What do you mean? The perturbations trying to influence the background?
Yeah.
Or
well, I guess I'm not an expert in the topic at all, so I'm just shooting that there's some relation there.
What back reaction are you worried about?
Back reaction when you have the, like, we'll say the void modeled as a fluid and dust.
Say that again. What?
And when you have the void modeled as a fluid and dust and matter, and they interact, the kind of, you have the interaction between the void underdensities and overdensities.
Well, interaction between underdensities and overdensities is all included in these equations. Okay, so my linear field is some arbitrary random Gaussian field that we have arbitrary underdense or overdense regions, respecting that symmetry, of course, for a Gaussian field. And once it becomes nonlinear, then you can see they are talking to each other, right? Because they are coupled through these kernels. And so this interaction between underdense, overdense regions, their shapes, it's all included in these mode coupling functions, okay? Which describes this physics that we just discussed, okay? So there's a piece which is a spherical collapse, a piece which is a displacement, and a piece is change in shape. So that's the change in shape in particular is the tidal field is affected by what the other overdensities and underdensities are doing compared to the one you're looking at. So this is all included.
Okay. Yeah, okay. I might try and ask the question again.
Yeah, we can ask, we can talk again after
There's
in
one
coffee.
question here. You,
Thanks for the lecture. Would you mind explaining again why only the monopole term survives in that passage?
Yeah. So here we are doing this integral, right? This 3k1, this 3k2, right? So, but this doesn't depend on angles, right? So I can write this as k1 squared dk1, k2 squared dk2, and 4 pi, and the solid angle between vectors 1 and vector 2. So this will be d cosine dk1 dot dk2. Does that make sense? And so this is just the integral, the measure that makes the Chandra polynomials orthogonal. Yeah, sorry, I went fast there. I was running out of time, but that means the monopole is the only thing that enters. Yeah.
Thank you for the lecture. Can you explain again, like, how to consider the pairs when you calculate delta cubic? I didn't get it.
Sorry, say that again, how?
Can you explain again, like, how to consider the pairs when you calculate delta cubic?
The pairs.
Yeah,
Yes.
the pairs.
Good. Yes. So there are three possibilities, right? So I can have delta of k1, so let me put the 1 there. Okay, they are all delta 1s, so I'm just putting the argument there. So I can have this. So that's one pair,
Okay.
right? I pair this with this and that with that. Second, I can pair k1 with k3. So that means I have to pair 2 with 4. Last one, I can pair 1 with 4. So then that pairs me 2 with 3. Does that make sense so far?
Yeah.
Okay? Now I claim this one is 0, right? Because you see, when I pair this with this by translation invariance, k1 and k2 add up to 0, and that makes this guy equals minus that guy. And the F2 kernel in that configuration vanishes, if you look at there. Okay? Look at here. 17 over 21. If I evaluate this at -1, the scalar product is -1 when the two vectors are exactly opposite, right? This evaluated at -1 is 1. 421 plus 17 over 21 is just 1. But this is the dipole. You see, I get a -1 here, and I get a 2 here, 0. Okay? And physically, that's because what I'm doing when I do that, I'm calculating expectation value of delta 2. It has to vanish because this guy has 0 mean, so this has 0 mean, this has 0 mean, this has 0 mean, everybody has 0 mean. Okay? And so the only two pairs that enter are these two, right? But they differ by exchanging 3 with 4. But exchanging 3 with 4, that's the linear theory, is these two guys, which are identical. So both can give the same answer, so I get a factor of 2. And then I just consider one of the pairings, okay? And that's the answer for one of the pairings, because then this will be power spectrum 1 with a Dirac delta between K1 and K3, this power spectrum 1 with a Dirac delta of 2 and 4. That would set this guy is equal to 0 and give me that.
Oh, got it. Thank you.
Yeah.
Professor, thank you for your lecture. What characteristic of the fluid, in addition to gravity, can contribute of the non-linearity?
What features of the fluid can contribute to nonlinearity? Or
what characteristic
yes,
of the fluid, in addition gravity,
in addition to
can
gravity,
contribute to the of non-linearity?
nonlinearity or non-Gaussianity?
Non-Gaussianity, yes.
Okay, good. So tomorrow we'll address that. So this is the piece of nonlinear physics that generates non-Gaussianity when we have matter alone. Okay. Tomorrow we're going to talk about what happens when you look at galaxies. Galaxies, they follow approximately the matter, but not exactly. So there will be a non-linear relationship when you go from matter to galaxies. So the lesson of today is nonlinearity generates non-Gaussianity. So when we go from matter to galaxies, we will generate additional non-Gaussianity. And then on Friday, we will observe galaxies instead of unfortunately, in galaxy surveys don't come with perfect measures of distance. We are actually, we measure things in redshift space, and they're affected by peculiar velocities. The relationship in going from actual space to redshift space is also nonlinear. So there will be also additional non-Gaussianities coming from what we call redshift space distortions. So at the end, we will have lots of non-Gaussianities to study, okay? And our job is to understand all of these and try to learn if actually the primordial field, delta 1, is non-Gaussian. That will be fantastic. We will learn probably something about inflation. So far, we haven't seen any evidence of that. Yeah.
Thanks, Professor. I'm confused with that equation, which is delta K1, delta K2, delta K3. Which term you put inside, then you get the bisect spectra?
Yeah, yeah, good question. So here I'm sorry, I should have said that I'm calculating again things to leading order. Okay, so what I forgot here, this result is, now I'm approximating this by the leading order, which is one of them is second order. The other ones are first order. And then all the possible permutations, right? Then this guy can be the second order, and then this guy can be the second order. So that will be the three terms that here they are all equal because I'm calculating everybody at the same point. Okay?
Yeah.
So that's what I'm doing here. I'm doing exactly the same thing that I did there. And then the only thing that enters is this F2 kernel. Same thing happened there.
Okay, okay.
Yeah.
I have another question. For the bisect spectra, have the relationship with the distribution, the distribution, this distribution?
The relationship to this?
Yeah, yeah.
Yeah, you can see from here when we calculated the skewness, right? This number is coming from this guy, right? From the monopole,
Yeah.
right?
Yeah.
So this asymmetry, the F2 kernel already describes to leading order how this PDF shifts to the left. Okay? So it's already telling you something about the shape of the distribution. It's also generating some non-Gaussianity here, so it's actually more complicated, but
Okay,
yeah,
okay. Yeah, thanks.
it affects everything. Yeah.
Okay, so I don't see any hands. So let's thank again Roman.